Hello, the next lesson is about the chain rule, and the chain rule is used for taking a derivative of a composite function. So remember, with a composite function, we have a function inside, completely inside of another function. So if you misidentify that, you're going to have trouble with these. The idea behind the chain rule then is if we do have a composite function where one function is clearly inside of another one, if we want to take the derivative, what we're going to do is we'll ignore the inside basically and take the derivative of the outside function. We'll plug the original one back in and multiply it by the derivative of the inside. We can see this if we work it out using this notation, the Leibniz notation, dy dx, where we treat the inside as g of x, we treat it as u. If we do that substitution, then our variable would become u. We can treat that as a derivative dy du. Then we would multiply that by the derivative of g of x, which is now u is equal to g of x, so it's going to give us a derivative du dx. And so if you think of these as fractions where the units are canceling out, it's kind of like the du and du are canceling out. Now, an easier way to think about this is the outside-inside rule. Just say to yourself, as you're doing, we're taking the derivative of the outside, so we're identifying what our function is that's on the outside and the derivative that's on the inside. So we take the derivative of that outside function, keep the inside the same, and then multiply everything by the derivative of the inside. Okay, so let's work this out with an example. We've got the sine of 5t minus 3. And this one, they're asking for the velocity, and if this is position, we need to take a derivative. Okay, so we know the derivative of sine of x. That's not a problem. We know that that derivative is going to give us the cosine of x. Problem, though, is that we don't just have x in here, and so we need to use a different rule when we take this derivative. So what we're going to do, we're going to treat the sine of x, the sine part, as our outside, and so if we're going to take our derivative here to get the velocity, we take the derivative first of sine, which will give us cosine. But then we're going to take the inside of this, the 5t minus 3, and we keep it the same, but then we multiply by the derivative of the inside. Derivative of 5t minus 3 is 5. Okay, here's another example. We're going to do it both ways. We're going to start by just expanding it first. So if we're multiplying this out, that'll give us 9x to the fourth minus 6x squared plus 1. We take the derivative dy dx is equal to 36x to the third multiplied by 2, so just using the power rule here, and then plus 0. Now if we'd use the chain rule here, and it's kind of optional because this isn't a difficult problem, but if we use the chain rule, we could just start from we wouldn't have to simplify before we start. We look at the outside function being something squared, the inside just being whatever's in the parentheses. So I'm going to start by thinking, what is the derivative of this part? It's kind of like we're covering up the inside, not even thinking about it. We're thinking like, if this was x squared, what would be my derivative? Well, my derivative would be 2 times x. Well, it's not really x inside of there. It was 3x minus 2, or 3x squared minus 1, sorry. We have 3x squared minus 1. Now, since we're using the chain rule, we'll now multiply that by the derivative of the inside, which is 6x. And then we can simplify this by multiplying everything out, which gives us 36x squared minus 12x. And so we end up with the same answer either way. Now with a polynomial function like this one, it might be up to you to make a choice, but in a lot of functions we will need to use the chain rule. When we're using trig functions, we need to use the chain rule because all of our rules are about just having x in here. So I'm going to start out this one by identifying my outside function. In this case, it's cosine. And so I think of that as if this was cosine of x, what would it be? So derivative of cosine is negative sine. Then I need to think about what's on the inside. The inside here was 3x to the fourth minus 2. So looking at that, I think about the chain rule. I've taken my derivative. I need to first keep it the same, and then I multiply by the derivative of what's inside. 3 times 4 gives us 12x to the third. And then we can simplify that. In this next example, we'll look at repeated use. Sometimes there's more than one, there's a composite inside of a composite function. For example, with this one, if we break it down, we'll notice that inside of there, first we can treat the root as a power, the 1/3 power. And on the inside we have the sine function, which, since we have x squared inside, is also a composite function. So we're going to take this one piece at a time. Basically, I'm going to start by thinking about this as anything to the root, a root of something, so, or to a power. So if I think this as x to the 1/3, I would have 1/3. I subtract my exponent by 1, which is giving me negative 2/3 there. And then I would just copy the inside exactly as I have it over here, which was sine of x squared. Next, since I'm using the chain rule here, I have to think about the derivative of the inside here. And so if I'm thinking about the derivative of the inside there, we're going to take that sine of x. Again, I'm going to think of this x squared as if it was not there. If it was just sine of x, that would give me a derivative of cosine. And then we would need to repeat the exact same thing in there. So in this one, I'm just going to write that x squared. Now again, I have something inside that is not just x, and so that'll lead me to my next step. I need to take another derivative here, which gives me 2x. Now sometimes students are a little confused about when to stop. Basically, you stop when you get to something. I know what the derivative of this is. If I take the derivative of x squared, that gives me 2x. I don't need to use another link of the chain. The only thing that's inside here, if I was thinking about taking another link, is the derivative of x, which is just, well, 1. And so it would just be times 1. So we could do that, but it would be a waste of time. When you get to a derivative that we already know, we can stop. Same thing if I had cosine of x on the inside. I would just take its derivative. I would get negative sine of x, and I'm done because it's a known derivative. Now to finish this one, we would just go ahead and simplify it like that. Sometimes we have to take multiple links to get where we want to go. If we look at this one, we're taking the derivative here to get g prime of t. We think first about our outside function. Now clearly tangent is the function with all that rest of that stuff inside of there. So the derivative of tangent is secant squared. Okay, and then I'll put parentheses here to write in whatever we have on the inside. Okay, so getting rid of this, I have on the inside 5 minus sine of 2t. Now from that, since that's clearly not just x, we need to take the derivative of that inside. And here the 5 would be 0 minus sine. Now we do have an extra 2t there. We're going to kind of ignore that for the moment. And we're going to start out with the negative sign. Derivative of negative sine would be negative cosine. And then we think about what's inside. And there I have 2t. Now our derivative would be if that was just x, so I need to think about this now. Its derivative would be 2. And so again, I could multiply all this out to simplify it. Maybe move the 2 out front and the negative. So now I have negative 2 secant squared 5 minus sine of 2t. Notice that's all inside of secant, so I can't combine it with the next part. And then times cosine of 2t. Also remember, this is secant, and we could think of that as 1 over cosine squared of all of this, but that would not cancel out with this cosine because the inside is different.